Hello everyone, I'm Dixin Tang. I'm happy to share my research in supporting user-centered analytical interfaces at scale. Many data analytical tools are built for people who have no or limited programming experiences, ranging from data scientists to data analysts and all the way to domain experts. Example tools include spreadsheets, visual analytical tools, and some Python data analysis libraries like pandas. To simplify data analysis, these tools typically provide intuitive and easy-to-use interfaces, which I call user-centered analytical interfaces. For example, spreadsheets provide an in-situ programming environment where people can easily express the computation by writing formulas along with the data. In a visual analytical tool, users can drag and drop to visualize data without writing one line of code. Some Python data analysis libraries like pandas provide a rich set of functions tailored for data scientists to easily analyze data. As a result, these tools have large user base. Spreadsheets have 1 billion users. Visual analytical tools are adopted by more than half of software companies. Pandas is also widely adopted by data scientists. Its popularity today is the same as Python's popularity in 2016. As user-centered analytical interfaces are widely adopted, another trend is that large datasets are available to more and more people. In many cases, they need to analyze datasets as large as hundreds of gigabytes or even larger. This is because the advent of data sharing techniques has helped many people to share their data with others. For example, data lakes have been widely adopted by people to share data. In addition, the development of data discovery techniques has also helped many people find their data they need. As a result, the general public now has an unprecedented need for analyzing large datasets. In face of large datasets, they still want to use their familiar interfaces such as spreadsheets, visual analytical tools, and pandas. Unfortunately, there's a lack of research for supporting these interfaces at scale. Existing tools or systems suffer from significant problems when processing large datasets, which span the full data analytical stack. These problems include interactivity, scalability, and resource utilization. Let me introduce each problem separately. The first problem is interactivity of visual interfaces. This problem comes when the system is updating the visualizations and the user is concurrently reading and exploring the visualizations. This concurrency often leads to limited interactivity or incorrect insights. Consider this example where the visualizations are computed from the data related to state Illinois. In a dashboard, it is common for the user to modify the filter and explore another subset of data, like the data for California. The system therefore needs to compute the new results and refresh the visualizations, which can take a long time under large datasets. During the refresh, some existing tools will hide all of the visualizations and the user cannot interact with them, which significantly hinders data exploration. Some other tools mitigate this problem by only hiding visualizations on the computations, but still have limited interactivity. The third option does not hide anything, but the user will see incoherent results. Some of them are computed from the new filter, and the rest of them are computed from the old one. And with incoherent results, people will get incorrect insights when deriving these insights from multiple visualizations. More critically, existing tools provide fixed solutions and not customizable to specific applications, although we have seen clear trade-offs across different options. So the question is, can we build a framework that supports the customization of properties and performance for presenting visual results? To answer this question, I extend data transactions to model this design space while additionally considering the user-related semantics. The second problem is scalability of query executors. Some existing tools, like pandas or spreadsheets, can only execute on a single machine, and the supported set size is limited to the memory capacity of a single machine. When the data becomes large, those tools become unusable. Even when the data can fit in the memory of a single machine, some tools like pandas are single-threaded, and cannot leverage the power of multiple CPU cores to reduce the data analysis response time. As a result, in face of a large dataset, the scientists can only analyze a sample of it and need the help of another data engineering team to analyze the full data. Here, this data engineering team will manually translate the program from this scientist into a new one that can run on a large-scale data analysis framework, such as Ray or Spark. This manual translation significantly consumes human resources. Ideally, the scientists should be able to analyze available data without worrying about scalability problem. So the question is, can we transparently scale the execution of pandas and spreadsheets without changing their interfaces? But the challenge is that these interfaces have unique data models, APIs, and access patterns compared to relational databases, which requires adapting traditional parallel execution techniques in databases to consider this new context. In addition, I have developed novel rewriting rules and the data compression methods to further reduce the data analysis response time. Finally, let me briefly describe the resource utilization problem. Many user-centered analytical interfaces are supported by databases, like the dashboard. Many dashboards are supported by databases. But it is still hard for end users to manage resource utilization in a database. As data analysis moves to the cloud, end users often suffer from excessive billing costs. Ideally, they should be able to explore the trade-off between performance and resource consumption and specify a performance goal to control the corresponding cost. In addition, existing databases are not optimized to be resource efficient, which means for the same response time, they spend much more computing and memory resources than they should. As we have observed, the available resources cannot keep up with data to be analyzed. Keeping using existing databases will not be environmentally sustainable. So the question is, can we build a database that minimizes resource consumption while meeting a performance goal that is specified by the user? Building this database requires revisiting several classic tactics, such as multi-query updation, materialized view reuse, and more. Overall, my research is to transform modern data analytical stack to efficiently support user-centered analytical interfaces at scale. For the interactivity problem, I developed Transactional Panorama, a framework that supports a combination of properties and performance for presenting visual results. To improve the scalability of pandas, I developed decomposition rules to parallelize pandas execution in a system called Modem. Modem has 7,000 daily downloads and 8,000 GitHub stars. In addition, I've developed toggle and formats for efficient spreadsheet execution. For the resource utilization challenge, I designed CrocodileDB, a resource-efficient database that leverages novel system strategies to reduce resource consumption while meeting a performance goal. Technically speaking, my research takes the big ideas in databases and adapt them to the setting that supports user-centered analytical interfaces at scale. The big ideas I've adapted covered many topics in database systems, such as database transactions, many query optimization techniques, parallel execution, and more. In addition, I've refactored the key components of several widely adopted data tools or data systems, such as Postgres, Spark, and Superset, which is a visual analytical tool. In addition to the aforementioned projects, I've worked on two others. The first one is adaptive concurrence control. Its idea is to host multiple concurrence control protocols in a single system and use each protocol to process the part of the workload it is optimized for. As workload changes, it leverages machine learning model to reconfigure the protocols. The second one is logs, a visualization recommendation tool. Logs provides a lightweight intent language for people to express the portion of data they're interested in, and automatically recommends the related visualizations based on predefined rules. Logs has over 4,000 GitHub stars and 400,000 downloads in total. Overall, the big picture of my research is examining the relationships between performance, resources, and system or user-facing properties for large-scale data analysis. Thanks for listening. If you have any questions, please send me an email. Thanks.